So last couple of classes we were discussing chromatic dispersion or group velocity dispersion. Right? We saw sort of how it's determined by the material and the waveguide components, and basically that the broadening of the pulse depends on this dispersion coefficient, right, which we can calculate for a particular type of fiber, and then the length of the fiber and the bandwidth in the signal, right? Uh, so um, today we'll sort of discuss this dispersion in a little bit more mathematical detail, and in particular look at the case which is sort of commonplace in the modern day telecommunication systems, is where we use a source which is basically a single frequency laser, right? So the actually source itself does not have or has negligible bandwidth. Okay, so in that case, like, how does dispersion happen, right? So recall we saw that this broadening, right, went as sort of this dispersion coefficient times the length of the fiber times the bandwidth in the signal, right? So this is in wavelength units. You could equivalently write this in frequency units like this, right? And then from here we saw that this figure of merit, if you look at the bit rate times the transmission distance, that's bounded by right 1 over this dispersion coefficient times the bandwidth, right? So we discussed various cases last time. For example, if this d, how this depends on wavelength, and then we can operate, right, like close to the zero dispersion point where the wavelength where this d is zero, right? So then now you start getting limited by the next higher order dispersion, third order dispersion, right? Equivalently, we can see here that what if this delta lambda was, let's say, zero or very close to zero, right? You would think that even then, right, as we take delta lambda to zero, we can get very high data rates and over long distances, right? And as this approaches zero, maybe we can like boost this up more and more, right? So as we keep reducing, as we keep making the laser closer to a single frequency source, right? So the spectrum is like a delta function. So this bandwidth of the source goes to zero. In that case, we can keep boosting up the data rate, right? Of course, that's also not true, right? Just like when we push d to zero, some other effects start to come in. Similarly, you'll see that if you start pushing this delta lambda to zero, so modern day lasers which are used in communication, actually, this delta lambda is very small. So this is sort of in the 1 to 10 femtometer range, right? In wavelength, on frequency units, this is sort of like the line width is a megahertz or less. Okay, so that's as close to zero as practically possible. Okay, so then the bit rates that you can get just from this formula would be like hundreds of terabit per second or something. Okay, but that's actually not true, because we'll see that again this formula will not hold anymore, because now we'll see that this bandwidth starts depending on actually our pulse itself. Okay, so now the source does not contribute any bandwidth, but since we are modulating the laser or the transmitter, right, and we are sending pulses of certain duration, you know from Fourier transform relations that any finite time limited signal will have some frequency spread of frequency components, right? So again, recall why was dispersion happening, right? So if you, let's say you have some fiber of length L, so now here we have a transmitter, right, which is sending out light at with certain bandwidth, right? So there's some center wavelength and some spread of wavelengths or equality frequency, right? So this delta lambda is basically what we will use, right? So again, for example, so for LEDs, this delta lambda is sort of like, let's say 10 to 15 nanometer. So here again we are talking about center wavelengths in the range, let's say 1.3 to 1.6 micron, the telecommunication wavelengths, right? So and then we have laser diodes, which are sort of free running semiconductor lasers, not stabilized. So they have sort of line widths, let's say between 1 to 10 nanometer, right? And then we have these single frequency lasers, where now delta lambda is basically in this range, so it's really small, right? In the nanometer scale, right? Right. So for these sort of incoherent broadband sources like LEDs or laser diodes, we can directly plug in this source bandwidth here to obtain this figure of merit. But for single frequency lasers, it doesn't. This formula doesn't work anymore, right? It doesn't mean that we can get as large bandwidths or over as long a distance as we can imagine. Something else, or we'll see what starts limiting. Right. So what we do here at the transmitter end is, right, we have some modulator, so we put the electrical data onto this optical transmitter, right, and then we have pulses. So let's say some bit zeros and ones, which we are sending. So now if you look at the temporal waveform here, right, it has some duration given by whatever bit period we have, right? And so if we look at an incoherent source like LED or laser diode, then the spread of frequencies, right? Basically, what we can imagine is that this spread, these frequencies are sort of distributed. So if I divide this into different bands here, right? So let's say lambda 1, lambda 2, lambda 3, up to some lambda n. So these frequencies are present sort of, so they all contribute a fraction of the power of the pulse. Okay. And basically, once now I send this pulse through the fiber, basically we saw this d or beta 2. What that is basically group velocity dispersion. So different wavelengths traveling at different speeds. So at the output, what happens is, so depending on again the sign of this d or beta 2, like the lower or the higher wavelengths will travel faster, right? And then now there'll be a split in time of these different wavelength bands, right? Which will lead to this broadband. Right, and so whether lambda 1 comes first or lambda n comes first, so whether this is an increasing wavelength with time or decreasing wavelength with time depends on the sign. Right. I mean, same thing if you look at, we can also say that different frequency components are. So I can also look at the spectrum in terms of frequency, right? Omega, or I can say different frequency components are also. So higher wavelength means lower frequency, or lower wavelength means higher frequency. So this would be sort of, so omega 1 sort of like here, I guess. right? So basically what's happening here is that so this TB or some pulse duration tau p, this source bandwidth, or if I look at it in terms of frequency, delta omega is much bigger than inverse of the pulse duration, right? Or the source bandwidth is much bigger than the bit rate equivalently. Okay, but now if we go to these coherent sources, right, like single frequency lasers, so there what's happening is now so the source itself, right, if you just look at the transmitter without modulating the electrical data, so it's just giving me sort of almost like a perfect sine wave at some particular frequency omega naught. So if I look at the spectrum, it's almost like a delta function, right, delta or in wavelength, right, and lambda naught. Right, so now basically we have the opposite case where the source bandwidth is much less than the bit rate or the, right, so again recall the bit rates we are talking about here. So the bit rates typically we are talking about are like, let's say 10 to 100 gigabit per second, right? So the bit periods or the pulse widths we are talking about are so 100 gig, so this 10 to 100 picoseconds, right? That's the sort of time scale for these pulses we are talking about. Okay, so you can see, so the line widths here in frequency for these lasers are like megahertz scale, and the data rates we are talking about are like gigahertz or tens of hundreds of gigahertz. So we are in this limit, right? So actually, if we now look at the modulated data, so after we made pulses here, so the spectrum after modulation is determined by the pulse width itself, right? So now you know. Okay, so going back to this incoherent sources, if I look, so this is the envelope of the pulse, right? Or let's say this is the power variation with time. If I look at the actual electric field, how the amplitude of the field is varying within this pulse. Okay, so for these incoherent sources, it actually looks sort of random. Okay, so there are like amplitude and phase fluctuations all over the place within this envelope, right? And that is what is basically giving me these broad spectrum, okay, for these incoherent sources, because the frequency and the phase is fluctuating all over the place, right? So the actual electric field with time looks kind of random with an envelope like this. So now if you go to these coherent sources, basically what you have within the pulse here is a nice single frequency, right? A single carrier frequency omega naught. So the pulse itself now, the electric field looks like a nice oscillation at omega naught with this envelope. Okay, so now what we can do is, so now the source bandwidth is negligible, but this signal here has some bandwidth, right? This pure sine wave which goes to infinite extent, that has sort of zero bandwidth. But once you make pulses out of this particular signal has some bandwidth, right? So now if you take a Fourier transform of this pulse here, you'll see that so this is like some envelope A of t, right, which might have some Gaussian shape or something, multiplied by a carrier frequency at omega naught, right? So the spectrum will be centered at omega naught, right, and it will have a spread here, which will be just sort of the inverse of the pulse duration here. Right, just from Fourier transform relations, you know that a signal which is which has an extent in time of tau, then its Fourier transform will have a spread in frequency which is 1 over tau. Okay, so now this is my signal spectrum, right? And now you can see that the bandwidth is determined by the pulse duration or by bit rate itself. Okay, and effectively now this bandwidth will see the dispersive effect, and similar thing will happen here, right? But since we don't have different frequency, we have only one carrier here, right? So the pulse after propagation, what it will look like is basically this carrier frequency will have an instantaneous frequency which is changed. Okay, so either this instantaneous frequency will decrease again or increase with time depending on the sign of the. So this carrier frequency will increase or decrease with time depending again on the sign of this. Okay, so this is known as a chirped pulse. Right, so this kind of pulse where the carrier frequency is does not vary within the pulse, that's an unchirped pulse, or we'll see also known as a transform limited pulse. When such a pulse travels through a dispersion medium, basically at the output what you get is a chirped pulse, where the instantaneous frequency now is a function of time. Right? So either increasing or decreasing depending. So if I plot omega of t versus t, it's actually like either increasing or decreasing. Right? So positive chirp or negative chirp, and so this almost looks like a Doppler signal, right? So when you have a train or some car with a siren approaching you, you see the frequency increasing with time, right? So it looks like this. So that sound that you hear, that's a chirp, okay? And yeah. So basically, I hope physically you understand what's happening, right? So you can see that even for ideal sources here, you still have some broadening which will now be determined by the bit rate or the pulse width itself. So we can't just boost this up by decreasing this further, right? So once my source bandwidth goes below the bit rate, then basically we are not gaining anything in terms of compensating for dispersion. Right? Of course, like for some other things like coherent communications, where we are, you might have heard about modulation schemes like phase shift keying or potential amplitude modulation. So these kinds of schemes are coherent schemes where this very narrow line width helps. Okay, so we'll see that later in the course. But just in terms of if you are doing this simple on-off keying, intensity modulation and direct detection, and we're looking at dispersive effect, then once my source bandwidth goes below the bit rate, then making it narrower and narrower doesn't really improve things. Okay, so we'll basically discuss this in mathematical detail, how to calculate how this pulse is evolving, right? And then from that, calculate how much broadening is taking place, because we can't directly use this formula, as I said, anymore, right? For once the source bandwidth goes very small. Right. So, Right, so again, let's take a pulse here, right? So it has some envelope, right? So this is the electric field amplitude. So basically I'm plotting the electric field. So let's say this is at the input of the fiber. So if Z is the distance along the fiber, right, let's say total length L, right? So basically now our pulse, my pulse has a shape which is function of time, and that shape will change as I look at different Z or different propagation distances along the fiber. Right? So this electric field is a function of both position along the fiber and time. So if I look at the input, right? So if I look at the, let's say at the input, I'm starting with an unchirped pulse like this, right? Where the carrier frequency is omega naught, right? And this envelope is like some kind of Gaussian. So the electric field amplitude I can write at Z equal to 0, which is the input, as again some. So this envelope has some function A of t, and then I have a carrier which I can write as e to the I minus I omega naught t. Okay. So whether I take a plus or minus is again convention, right? So you know this wave is propagating towards positive Z, right? So starting from Z equal to 0 to Z equal to L. So that kind of wave, you know, I can write, so for example, as, so if beta is the propagation constant, I can write it like this, right? So if I use this convention, basically that's why I'm writing in front of the temporal term here, I'm getting a minus I. Okay, I could equivalently write it as omega t minus beta Z. Okay, the physics will come out to be the same, right? So either you take a positive sign in front of the spatial coordinate and a negative in front of the temporal, or the other way, right? So here we are taking this convention. So that's why they do this. Okay, and so this envelope here is some kind of, let's say, a Gaussian pulse, right? So for example, it looks like something like this, right? So this is a Gaussian function in time, right? Tau p is sort of the, you can see sort of like the half width of this pulse. Okay, and if I look at the power or the intensity in the pulse, it will be something. So if I take the mod square of this, right, that gives me the power. So you can see that will look like a Gaussian function here, right? So of course the power does not have any phase; it's just a pure real number, right? So looks like that. Okay, so that's my input pulse here. So now again, this is a finite extent pulse in time, so that means I mean it will have some spread in frequency. So if I want to calculate what this spectrum is here, right, at the input, so I can just take the Fourier transform. Of the input pulse, right? So, you know, this is just like that. right? And again, there is a convention here whether you want to take plus or minus. If you take a minus here, right, then in the Fourier transform formula, you have to take a plus here for the temporal integral. Okay, if you take the plus here, then you have to take minus. Okay, so we basically plug in this form for the input pulse. So you see, I get now here the input envelope, then multiplied by e to the I omega minus omega naught t, right? This coming from here. So you can see that this now looks like a Fourier transform of A, which is the envelope. Right? It doesn't see the oscillation, just the envelope. Right? This is like a Fourier transform, but at a frequency omega minus omega naught. Right? So this is basically the spectrum of A. Right? So the spectrum of the electric field, total electric field at frequency omega, is the spectrum of the envelope at frequency omega minus omega naught. Right? It's just saying that. I mean, this is just what we are just sort of rewriting the basic simple Fourier transform rule, right? If you have some function, if you multiply by a carrier frequency, then you shift the spectrum to that frequency. So basically, I'm saying, so if E is centered at omega naught, then you will see that A, if I look at the spectrum of A, that's centered at 0. Right, of course, because it's a baseline signal. Right, but this shape is identical. This is just shifted. Okay, that's what it is. Right, and basically what we are interested in calculating is how this envelope is changing as a result of propagation through this dispersive fiber, right? Because we are interested in how much this is broadening and what are the limitations on the bit rate, right? So we are basically ultimately interested in basically this, how this envelope is changing, right? Because that is what is determining my like power extent and then determining when the next bit can come. Okay, so now we know that on propagation, basically you acquire a phase like that, right? So as you propagate in Z, you acquire a phase like e to the I beta Z. So now we have a spread of frequencies here, right? And you know that, again, going back to the fundamental reason why dispersion is happening is that this beta is actually a function of omega. So if I change omega, this beta changes. Right, so here if I look at the spectrum, each different frequency component will have a different beta. Right, because of beta was basically omega over c times an effective, which is also a function of omega. Right, so you can see that this is a function of omega from here and also from here. Why do we take the Fourier transform? I mean, because we want to know what the spectrum looks like, right? So if I have some signal in time domain, how do I find what is the spectrum? I take the Fourier transform. That's the way to find out the spectrum of any time domain signal, right? So you'll see that to find out how the pulse is changing in time, actually it's easier to first sort of take its spectrum and see how the spectrum evolves, and then go back, take an inverse Fourier transform again, and then see what the final time domain pulse looks like. Okay, rather than directly sort of trying to solve for how the time domain pulse varies. although we derived like a pulse propagation equation. Okay. But anyway, so for any time domain signal, we have a temporal waveform and a corresponding frequency spectrum. Right? So similar case here, and we'll see how each of these is changing due to dispersion. And this is straightforward, right? I mean, this you know again from basic Fourier transform relations. If I have a signal multiplied by some e to the I omega naught t, then I shift the spectrum of A to omega naught. Which see this from here. Yeah, right. So if I have now, so at the input I have an electric field amplitude, right, for each different frequency here. And now as it propagates along the fiber, each frequency component will acquire a phase, e to the I beta z, right, where beta for each frequency will be the beta corresponding to that frequency, right? So in the spectral domain, I can easily write what after propagation distance z, what would be the change in the spectrum? It will just be a phase, right? So E at z and omega will be just the input spectrum multiplied by the phase. Right? Because that's the only thing that is happening. Right? I have this mode which is, so again, single mode fiber, LP01 mode is launched, and basically that mode is propagating. So as it propagates, it acquires a phase. That's all it's happening. Okay, and now if I want to see again, go back to the time domain and see how the temporal waveform looks like. So in the frequency domain, only thing I'm doing is adding a phase, right? But this phase is now frequency dependent, right? Each frequency here is getting a different phase because this beta is a function, right? So if I take actually the magnitude, that remains the same, right? If I look at this, for example, the power spectral density, how much power is present at each frequency, that is just the mod square of this, right? So that remains the same. That does not change due to dispersion, and that is sort of expected because dispersion is a linear effect, as we had discussed already. So it can't and also we've not sort of assumed any losses or anything. So basically, it can't change your spectral density or power spectral density. It can't change, you can't introduce new frequency components, or it can't exchange power between different frequency components. Right? So actually the power spectral density remains the same. Only thing which is happening is there is a frequency dependent phase. Okay, so now, yeah, to go back to the Fourier, time domain, I take an inverse Fourier transform. Right, so this is E of z omega. So since I took a positive sign here, I'll take a negative sign in the inverse. Right? And I just plug for E z of omega this. Right, and then I can further actually substitute for E0 of omega this in terms of A, because again, we finally want to see how the envelope is changing. Okay. And now what we do is, so we need to somehow compute this beta of omega, right? So that we saw basically, so that's given by like um, a contribution of the material and the waveguide dispersion, right? How basically this n effective changes in frequency. So what we do is we say that this bandwidth here, right, we saw was basically right. So here this roughly would be, as we said, inverse of the pulse duration here in time domain, right? Again, we are considering pulses here which are, let's say, tens of picosecond. So 1 over tau p, the bandwidth here is again sort of 10 to 100 gigahertz, right? And omega naught, the center frequency, you know, is just like the inverse of the, so this is 2 pi c over lambda naught, where this is, let's say, 1.5 micron or something, telecommunication wavelength. So omega naught is like 10 to the 15 per second or something, right? So the point is this delta omega is much smaller than omega naught. Okay. So typically we are operating in the regime where this delta omega, which is the inverse of the pulse duration, or basically something related to the bit rate, is much smaller than the carrier frequency. So for that, what we do is we can expand this function beta of omega around omega naught, right? So basically the omegas that we are looking at are in this small range around omega naught, right? Where the deviation from omega naught is, the fractional deviation from omega naught is very small, right? Delta omega by omega naught is, you can see here, like 10 to the minus 5 or something. So we can do a Taylor expansion about omega naught for these frequencies. Okay, so there will be a first derivative times omega minus omega naught, right? So beta 1 is the first derivative of beta with respect to omega. There will be a second order term beta 2 times omega minus omega naught square, right? Beta 2 is again the second derivative of beta with respect to omega, right? So beta 1 is 1 over the group velocity, right? So at omega naught. And this is basically the beta 2 GVD coefficient at omega naught. Right? Plus, I mean, I could include as many terms as I want. I could have a beta 3, right, which would be third order dispersion, etc., etc. So maybe I will just write that. So if I have beta 3, then that's beta 3 by 3 factorial, which is 6, times omega minus omega naught cube. Okay. So if I plug this Taylor expansion for beta of omega here, Then basically this E of z comma t I can write as some A of z comma t times e to the I beta naught z minus omega naught. Okay, so beta naught is basically this beta at omega naught, which is the propagation constant at the center frequency, right? So, so for this beta of omega, I'll have a beta naught. So I'll get e to the I beta naught z. So that's independent of frequency. I can just take that out, right? And I also take out a factor of e to the minus I omega naught t, right? So that means here I'll get a e to the minus I omega minus omega naught t, right? So this thing. So you can see down again this total electric field looks like something like like this is central carrier frequency, which is acquiring a phase e to the I beta naught z, right? Just as we expect, like a wave propagating at frequency omega naught, and then we have the amplitude, the envelope part here, right? So that envelope we can compute like this. So this is now something like a inverse Fourier transform of so in this Taylor expansion, beta naught we already took out. The next term is beta 1. Okay, so let's say we keep terms up to the third order, is beta 3. Then we have this in the phase factor here. Right? Okay, so where this capital omega is just the detuning from center frequency. Right, so we have beta 1 times omega minus omega naught. So that's beta 1 times this capital omega. Right, again, so if I look at the spectrum here, so the spectrum of A, right, as a function of omega is centered at 0. Right, whereas if I look at the spectrum of E, that's centered at omega naught. Right, again, way of rewriting the same thing. So now you can see that if I want to calculate what the envelope looks like at a certain distance z after propagation, then basically I start from the input spectrum, which is, right, so remember this is the Fourier transform of the input envelope. And then I multiply by this phase factor, which depends on my dispersion coefficients. So beta 2 is we call the GVD parameter. This is third order dispersion. And then I take like an inverse Fourier transform to go back to the time domain. Right. So basically, what dispersion is doing here, you can see, is just it's imposing a frequency dependent phase on the spectrum. Right. That's what dispersion is doing. And this frequency dependent phase basically leads to this temporal broadening and also this chirping that I was talking about, right? A time dependent instantaneous frequency. Right, so you can see basically that's why we sort of go into this frequency domain, because in the frequency domain, the dispersive effect is just a multiplication, right, a phase factor. Okay, so basically our task is to sort of get some propagation equation for this pulse, right? So to get some equation for how this A evolves with Z in time domain. So here we sort of got some formula which is in the form of an integral. Okay. From this we can actually get some kind of propagation equation. Okay, so if I so this equation is A Z of t is equal to this, right? So this is the equation. So I differentiate both sides with respect to Z. Okay, so I get on the left side. So now this is, I decide this integral with respect to omega. So multiply by e to the minus I omega t and integral over, I already have d omega there. Over omega, I just write as inverse Fourier transform. Right? So inverse Fourier transform means this operator 1 over 2 pi integral of d omega e to the minus omega t. And so now when I differentiate this with respect to z, you can see z is coming here in the phase factor, e to the I, this function of omega times z. Right? So when I differentiate with respect to z, this factor will come out front. Right? So I have beta 1 omega plus there's an I here also. Times A of 0. Right? No, that just is Z. Because so when I take differential of this e to the I this times z, I'll get this out front and then again e to the I this times z. Right? So this complete thing will remain, right? So this is basically A Z omega. Right? The spectrum of the amplitude at distance z. So that's what it is. Right? And this factor just comes out front. Okay. So now you can see that I get terms like, so I have, for example, if you look at the first term, that's like the inverse Fourier transform of some I omega times A omega. Right? So just the inverse Fourier transform of A of omega is A of t, right? If I multiply by this I of omega, you know that this is just dA by dt. Right? Because again, this is basic Fourier transform relation. So A of t, if I write as A of omega e to the I guess there's a minus sign here. Right, so if I take derivative with respect to time on both sides, then you see here I get a minus I omega A omega. Right? So the inverse Fourier transform of I omega times A omega is dA by dt. Right? And now I can take another differential. So you can see that then I'll get square. So the second term here, omega square, will be the double derivative of A with respect to time. And similarly, this third term cube will give me the third. So whatever order I take up to dispersion, it will give me that many orders of derivatives with respect to time. Okay, so if I use these rules here, then basically this equation is, I can just write like this. Okay. So now I've derived some sort of equation here for how the amplitude, the envelope of the pulse A changes with distance Z. Okay. So it's a function of both position Z and time, right? And the equation with which it evolves is given by that. Right? So first term is just basically the pulse moving at the group velocity. Second term is basically this GVD term, which will give me broadening. And then the third order term, and so on. Right? So now let's say if we have a medium with no dispersion, which means that beta 2 and all higher orders are 0. Right? So let's say beta n is 0 for n greater than or equal to 2. So there is no group velocity dispersion and any higher order dispersion. Then the equation you can see here is just that, right? This should be a minus here. No, that is still plus. Because we have a minus here, then we take it to the other side, it becomes plus. Anyway, yeah, so recall this beta 1 was 1 over the group velocity. Right? So this is like dA by dz plus 1 over Vg dA by dt. Right? So that's an equation of a pulse which is moving at the group velocity. Right? So right, so basically if you have something here A of t at the input z equal to 0, then at a distance z, right, you get the same thing delayed by Z over Vg. Right? So the pulse arrives at a distance Z after time Z over Vg. Okay, so basically, I mean, you can check this equation will satisfy this, right? So A of Z comma T minus Z over Vg is equal to A of 0 comma T. Right, so in the absence of dispersion, you just have a pulse which is moving at the group velocity. So now again, we are interested in how this amplitude, the envelope shape A is changing, right? So basically we go into a frame which is moving with the pulse, okay? So here basically this T is some universal clock that I'm measuring time, right? And yeah, so basically at some distance Z from the input, the pulse arrives after a time Z over Vg, right? So if I'm an observer at Z, and then I have my own local clock, and then I basically measure the pulse going by. If I want to reference the peak of the pulse, right, as time equal to 0, right, you can see that the clock of this observer at Z has to be delayed from this universal clock by Z over Vg, right? Or in other words, if I move to a frame which is moving with the pulse, right? So then basically I'm sitting in some frame which is also moving at Vg. Then I don't see the pulse moving, right? And what I see are just the changes in the shape, right? So basically, if I go to a frame, so-called co-moving frame, it's just to sort of make the equation and the mathematics a little bit simpler, because this group velocity term is just telling me that the whole pulse, sort of the energy is traveling at Vg, right? Which we know, and we are not worried about that, right? We are just worried about how the pulse gets broadened because of these terms. So we move to a frame right, where now I define the time as the universal time t minus this z over vt. Right? So now this time you can see depends on my position, right? Because this is the time that I'm measuring in the moving frame. So moving with the pulse, and z coordinate remains the same. The position is still the universal position. So we go to new coordinates t prime and z prime, which are functions of the original coordinates t and z. Okay, so now I'm only sensitive to changes in pulse shape. Right, so in this frame, basically what I'll see is that this shape is just sort of changing with time, but the pulse is always centered at 0 and it's not moving. Right, so we do this change of coordinates and write this equation in terms of this new coordinates. So, so this is also just t minus beta 1 z. Okay. So if I look at, so I have terms here del by del z and del by del t. So, so del by del z here you can see will just be del by del z prime. So there's no change in this term. But the time del by del t, you can see. So I can from here write t is equal to t prime plus beta 1 z. Anyway, so since now t is a function of t prime and z, I can write this as del t over del t prime times del t prime del t plus del over del z prime times del z prime. Okay, sorry, I have to do the same here, right? So I have to use the chain rule for both these terms. Okay, so if you look at this time term here, so del t prime by del t. So del t prime by del t is just 1. Right? And what about the other term here, del z prime by del t? Del z prime doesn't depend on t at all, so this is 0. So, right, so this is 1 and this is 0. So del by del t is just del by del t prime. And what about this term here? So del z prime by del z, that's 1. And then del t prime by del z. So here, del t prime by del z is minus 1 over bg, or minus beta 1. Right? Right, so del over del z, I can write as del over del z prime minus beta 1 times del over del t prime. Right, so I substitute these expressions for del over del z in terms of z prime and t prime, and also del over del t into this equation to get the equation in terms of z prime and t prime, the new coordinates in the moving frame. So yeah, so basically you can see, so for d over dz, I get d over dz prime minus beta 1 d over del t prime. So this minus beta 1 del over del t prime gets cancelled with this plus beta 1 del over del t prime. Okay, so that term just goes away. So I have del over del z time. This term goes away, cancels with this term, right? And these two terms are remaining. Okay, so that is my equation. So now you can see I am only sensitive to the dispersion terms. So the GVD second order term and higher order terms. I've taken out the group velocity. Right? And basically it's understood that typically that when we use this equation, we are in the co-moving frame. So we drop these primes here. And just write it in terms of sort of the original E and Z, but understand that these are the co-moving coordinates, not the usual. Or more specifically, this time is like the time within the pulse, right? So in the co-moving frame, this time is just, so t equal to 0 denotes the center of the pulse, right? And t less than 0 is the leading edge, t greater than 0 is the trailing edge, right? So this is not universal time, but like the time within the pulse, so in the co-moving frame. Okay, so this is the pulse propagation equation in terms of dispersion. So here, if we include up to third order dispersion, we get this. In general, you could include up to any order of dispersion. Okay, so basically the equation will be, so let's say if I want to include up to all orders of dispersion, then the mth order dispersion will have m factorial, the denominator, right? And it will be the mth order derivative. Of A. Right, so this is only if we include up to third order dispersion. This is all orders of dispersion. Right, so you can see the mth order dispersion is giving me the mth derivative of the pulse. Right, and yeah. So if these coefficients are 0, if beta 2, beta 3, beta 4 are all 0, then A does not change. You can see del A by del Z is just 0, which means A of Z is independent of Z. Right? So the pulse just moves without any change. But if any of these are non-zero now, then you can see that the A will, the envelope changes as a function of Z. Right, so yeah, so this is the pulse propagation equation to, if you want to see how a pulse moving in a dispersive medium evolves, right? And the solution we already saw, right? Actually, we came to this solution, to this equation from sort of the solution, right? To solve this kind of equation, what we do is go to the frequency domain, take the Fourier transform, right? And then we saw that we can just do a multiplication like a phase factor. So actually, that's how the equation is actually solved, right? Because to solve this complicated differential equation in the time domain is not straightforward. So what you actually do is actually do what we had done, right? So I start with some input, right? So this is my equation. I start with some input A of 0, comma t, and I want to find what is A of Z, comma t, right? So this is the equation which governs the evolution, but I can't solve this differential equation directly. What I do is actually, so starting from the input, I first take the Fourier transform to find the input spectrum, right? Then I multiply by the dispersive phase. To get the spectrum at Z, right, which is, we saw just phase factor. So you can see, so here this will give me beta 2 times omega square. Next term will give me beta 3 times omega cube, and so on, up to however orders you want to include, right, and Z. So the effect of dispersion in the frequency domain is very simple. It's just a phase. So I can easily do that, right? And then to find Az of t, I take the inverse Fourier transform. Okay, so this is how I actually solve this equation in practice. Right, so these beta 2, beta 3 are all determined by the type of fiber I'm using. Okay, so let's look at the solutions for a general case of these Gaussian pulses, but also having what we discussed where the frequency is not constant, but the instantaneous frequency could also be time dependent. So that's called a chirped Gaussian pulse, because we'll see that the effect that dispersion has on time domain is actually a chirp. And in general, right, the most general pulse that I could write is something like this, where the instantaneous frequency is also a function of time. Right, so and this chirp is that could be useful in actually compensating for dispersion, as we will discuss. And also, like some sources like the semiconductor lasers, when you actually directly current modulate them. So, for example, if you want to imprint, if you want to do intensity modulation, so you send high current for bit 1 and then low current for bit 0, so that the output power is low for bit 0. Right. So when you do this, actually, because of the sort of carrier dynamics happening within the semiconductor structure, there's automatically also a chirp induced. Okay, so not only do you have a pulse in with varying power intensity, but there is also some chirp introduced onto the pulse. Okay, so it's important to keep track of this chirp. So it's either coming from the input or introduced in my dispersive fiber, right? So if we understand how this chirp is happening, we can also use this to our advantage to compensate for dispersion, as we'll see. Okay, so a general chirped Gaussian pulse, right? I can write as, so this amplitude. Now, as we saw, so we could write, so for example, this as this would be an unchirped pulse, but if we include a phase factor here, like that, okay, if so, this capital C here is the chirp parameter. Right, so if this capital C is 0, you can see that this just looks like a simple Gaussian pulse, right, with sort of half width T naught. Okay, but if the C is non-zero, then you can see that this is like a phase on top of this pulse, right? So that phase factor goes as e to the CT square. Right, so it's a quadratic phase in time. Okay, so if there is a non-zero chirp, that means there is a quadratic phase, and you know the instantaneous frequency. So if I write this as e to the some phase phi of t, the instantaneous frequency I can write as the derivative of the phase. Right. So you can see that if I take the derivative of this will be linear with time, right? Because this is quadratic, so the derivative will be linear. So you can see now the instantaneous frequency will be linearly varying with time, and depending on the sign of this C, it will either increase or decrease. Right? If C is positive, then it's a positive chirp. Omega t increases with t. Right? So in this case, for example, you can see the oscillations are getting faster. Right? So that implies a positive C. Right? Negative C will be opposite. The minus sign here is again coming from the convention that we are using e to the minus I omega t as the temporal phase. Right. So okay, so this denotes positive chirp. Negative chirp will be the opposite. High fast oscillations here and slower slopes. Okay. So if I take a general chirped pulse like this, a chirped Gaussian pulse like that, I can again find the spectrum by taking the Fourier transform. Right. If I take the Fourier transform of this thing, so one thing to note is if I take the if I look at the power or the intensity, right? So that will just be the mod square. So that you can see just depends on T naught, right? So because let's maybe not go there, but we'll discuss that maybe later. But yeah, so if I want to find the spectrum, I take the Fourier transform of this, right? So this also is a Gaussian function. It's just a more generalized Gaussian function with sort of a complex number, right? So if we absorb this complex number into the T naught, this is like some minus T square by some complex tau square. Okay. So anyway, but you can use the same kind of integrals for computing the Fourier transforms even with complex numbers here. Okay. So I mean, you might know that like a Fourier transform of a Gaussian function is a Gaussian function again. So that holds true here even for complex numbers there. So when we take the Fourier transform, okay. Yeah, so that's what you get. Okay, so to compute this, like there are standard integral identities that you can use. Like for example, like I think this is something like this. Okay. So this minus ax square will come from the right. So this looks something like minus ax square, and then when you take the Fourier transform, you'll have a e to the I omega t. So that will be like the bx term, right? So this formula works even when a and b are complex numbers. Okay. You can use this formula to find the spectrum here. Take the Fourier transform, so you'll get that. Okay. So this complex part, this exponential part here, right? This is a complex number. I can write it as a real part and an imaginary part. So if I write it as like that. Okay, so there's a real part and an imaginary part, right? So the real part is giving me the power spectrum, right? And this is a phase, frequency dependent phase, right? So you can see a chirp pulse has a quadratic phase in time. It also has a quadratic phase in frequency, right? Omega square. And so if I take the spectrum, the power spectrum will be mod of this square, right? So this phase will go away, and the width in the spectral domain, right? If I like this, that's e to the minus omega square by some capital omega, right? These are capital omega. So if I write this as some e to the minus omega square by 2 delta omega square, well, delta omega is the spectral width, right? So then you can see from here delta omega is basically square root of 1 plus c square by t naught. Just comparing these two, right? So you can see that the bandwidth, right, of a chirp pulse right goes like this. Okay, so it depends on the chirp parameter and the temporal duration. Right, so again, if you take the power spectrum of this, that looks something like e to the minus t square by t naught square, right? So this is duration t naught. This is mod of a square, so the power in time domain, right? And then this is the power in the frequency domain, that there is a width to that, right? So this spectral width is related to the temporal width, like that, right? So again, from basic your signal sense systems or your transform, you might know this relation of the bandwidth being inversely proportional to the time, right? But here we see that to be more specific, this factor here depends on the chirp parameter. Okay, so you can see that. So if for a given bandwidth, right? So if I calculate the pulse width, which is a function of the chirp parameter, right? For a given bandwidth, right? It scales with sort of the chirp parameter like that, right? So, and what is the minimum pulse duration that we can have for a given bandwidth? That's for c equal to 0, right? This function is minimized for c equal to 0. So the minimum pulse width is for c equal to 0, which is so known as unchirped pulse. Right? And for that, the bandwidth is 1 over, the duration is 1 over the bandwidth. Right? What you sort of know from basic. Right? But actually, you see that if there is some finite chirp on the pulse, then the pulse duration will actually be longer than this 1 over delta. Right? So, a chirp pulse is always longer than an unchirped pulse for this if they have the same frequency content. So this unchirped pulse is also known as a transform limited pulse. Right, because it has a duration which is sort of great. minimum possible allowed by the Fourier transform. Okay, so now you can see sort of where this dispersive broadening is coming from, right? From here. So if I launch an unchoked pulse at the input, right? What dispersion is doing is adding this frequency dependent phase, right? So the beta 2 term, as we saw, adds a phase which is proportional to omega square, right? And once you have that, you can see that that's basically like a chirp. So when I go back to my time domain, there's a again a time dependent phase, quadratic phase, because of dispersion, right? And now and we already saw that the spectral content does not change, right? All that's happening is we are multiplying by phase in the frequency domain. So the power spectral density does not change, which means this delta omega, which is the frequency bandwidth, the pulse frequency content, that is the same, right? That's not changing. So on propagation, what's happening is this C chirp parameter increases as this phase increases on propagation. And due to that, this T naught, the pulse duration, increases. Because this is a constant in the denominator. Due to dispersion, chirp is happening, and due to the chirp, the pulse is broadening. Right? And you can see that it does not depend on, it just depends on C square. So it does not depend on the sign of the chirp. Right? It could be positive or negative. Both will give me broadening. So again, here, the dispersion could be positive or negative. Doesn't matter. If I start from an unchirped pulse, it will always broaden, right? Because an unchirped pulse is the minimum duration that is possible for that bandwidth. So it has to broaden, it can't compress. On the other hand, if I start with a chirped pulse, right? So now you can see that it's not, if I start with a chirped pulse, then it's not the minimum duration for its given bandwidth. So there is room to compress it, right? So if I start with a chirped pulse and I go through a fiber which has the opposite sign of dispersion, then it can actually compress. Okay. So yeah, we are out of time, so we'll discuss a little bit more of how sort of this chirped pulse we'll see using this recipe that we derived today. Right? We see how a chirped pulse gets transformed due to dispersion, and we can see then, depending on different inputs and different dispersion of the fiber, how the pulse will evolve. So, yes, we'll do that next time. Any questions? Okay, no questions, then we can stop. So as I had announced earlier this week, there'll be a class on Saturday. Can you explain the physical significance of first derivative of space? I mean, so that's coming because, I mean, recall how we derived that was basically we started from sort of this kind of procedure and we took the derivative with respect to z here, right? And basically our task is to find how this envelope is changing, right, as a function of z. Right, so we want some equation where you want to see what this dA of dz is equal to something, right? Because we want to find how A is changing with z. So turns out that a first order differential equation in Z is enough, right? And that comes because here the phase is linear with Z, right? If you had some effect where you had other terms like square of Z or something, then maybe you could have like second order derivative or something. But, yeah, so that's why in this case, like a first order differential equation in the spatial coordinate is enough to describe the path propagation. Compared to the wave equation, right? So again, if you recall, there's like a proper wave equation, right? Where you might have seen something like this kind of thing, right? So here you have sort of double derivatives. But then from here you can go to what is known as a paraxial wave equation. Under the condition of something known as the slowly varying envelope approximation, right? So from there you end up with an equation which is sort of linear in there, right? Under the approximation where under the approximation that the wave is not or the amplitude of the wave is not varying too fast, right? With respect to, for example, the wavelength scale, right? So if you assume that the amplitude does not vary, or the amplitude is negligibly varying over a wavelength scale of propagation, that's known as slowly varying envelope approximation, then you can sort of get rid of the second order derivative here and just end up with the first. Okay, so I guess something sort of similar we can do here. We went through this, if you recall, in the sort of, I think the fiber optics course, we sort of went through this detailed derivation of. There also we had, if I'm not wrong, probably derived some version of this pulse propagation equation, right? And there we, I think, went through this. But yeah, so that's related to sort of this phase is now just linear in Z, and there is no. I mean, of course, we've not taken any loss here. So only in very certain specific cases where you have interactions which are very intense, where the amplitude can change very fast, there you sort of include. But that's for in whole of optics, that's a very small fraction, maybe like I would say 0.1%, much less than 1% of the total problems in optics where we have to include maybe a higher derivative of it. But yeah, anyway, in these cases, it's not.